Welcome to a deep dive into one of the most promising technological revolutions happening right beneath our feet. Today, we're exploring how microscopic bacteria are being enlisted to solve a massive global crisis: our crumbling infrastructure. Concrete, the literal foundation of modern civilization, has a fundamental weakness that costs billions in repairs, causes countless injuries, and contributes significantly to climate change. But what if concrete could heal itself? What if our bridges, highways, and buildings could detect damage and repair it automatically, just like living organisms? This isn't science fiction, it's happening now, and it could change everything about how we build our world. The scale of our infrastructure problem is staggering. According to the American Society of Civil Engineers, 43% of America's roadways are in poor or mediocre condition. The repair backlog exceeds $786 billion, and that's just in the United States. This crisis extends worldwide, affecting developed and developing nations alike. The fundamental issue? Cracks. Concrete inevitably develops cracks, often microscopic at first, that allow water and chemicals to penetrate its matrix. This moisture reaches the steel reinforcements inside, causing corrosion and eventual structural failure. Traditional repair methods are not only expensive and disruptive but ultimately temporary, creating a costly cycle of maintenance that strains public budgets. Each year of delayed maintenance adds an estimated 15 to 20% to eventual repair costs. In developing nations, infrastructure failures can represent up to 5% of GDP losses annually. Beyond the economics, there's a human cost. Concrete failures contribute to thousands of injuries and hundreds of deaths globally each year. Our current approach of build, deteriorate, demolish, rebuild is unsustainable, filling our landfills with construction waste that accounts for nearly 40% of solid waste worldwide. The solution to this massive problem might come from some of Earth's smallest organisms. Scientists have developed self-healing concrete by infusing it with bacteria, typically Bacillus species such as Bacillus subtilis, Bacillus sphaericus, or Bacillus pseudofermis. The concept is elegantly simple yet revolutionary. These specialized bacteria are embedded into concrete during the mixing process, where they remain dormant, essentially hibernating within the concrete matrix. The microorganisms aren't just tossed in raw. They're carefully encapsulated in protective materials like clay pellets or hydrogels, alongside their food source, typically calcium lactate. This packaging protects them during the mixing and curing process, which can reach temperatures above 60 degrees Celsius. The bacteria can remain viable in this dormant state for up to 200 years, potentially providing healing capabilities throughout the entire lifespan of the infrastructure. When cracks inevitably form and water seeps into the concrete, something remarkable happens. The moisture awakens the bacteria, which begin to feed on the calcium lactate. As they metabolize this food source, they produce limestone, calcium carbonate, through a process called microbially induced calcite precipitation. This natural limestone effectively seals the cracks, sometimes within as little as 3 weeks, before water can reach the reinforcing steel and cause serious damage. This revolutionary technology didn't emerge from thin air. It was inspired by natural processes that have been occurring for millions of years. The bacterial calcification process is similar to what happens in limestone caves, where bacterial activity contributes to the formation of stalactites and stalagmites. These impressive geological formations grow extremely slowly as calcium carbonate precipitates from mineral-rich water, often aided by microbial activity. The bacteria used in self-healing concrete have evolved to thrive in highly alkaline environments, precisely the conditions found within concrete, which typically has a pH between 12 and 13. Most organisms would be destroyed by such caustic conditions, but these specialized bacteria have adapted to not just survive but flourish. Their ability to form endospores, a dormant, protective state, allows them to withstand extreme conditions including heat, desiccation, and the harsh chemical environment of curing concrete. When conditions become favorable again, in this case, when water enters through a crack, they reactivate and resume their metabolic processes. It's a perfect example of how studying natural processes can lead to technological breakthroughs that solve human problems. What makes this development particularly exciting is the scale at which it's now being deployed. This isn't just a laboratory curiosity anymore. It's being implemented in major infrastructure projects around the world. The Dutch firm Bacillus, founded by microbiologist Hendrik Jonkers, often called the father of self-healing concrete, has recently completed a significant highway section in the Netherlands. The A76 highway near Geleen now features what engineers call living infrastructure, concrete that can repair itself multiple times over its lifespan. Early data suggests these self-healing sections could extend the infrastructure's useful life by 30 to 50% while reducing maintenance costs by up to 60%. The applications aren't limited to the Netherlands. Chinese authorities have begun incorporating bacterial concrete in sections of the massive Belt and Road Initiative infrastructure projects, particularly in marine environments where traditional concrete deteriorates rapidly due to salt exposure. In Singapore, the Housing Development Board has begun testing bacterial repair sprays and injection systems on aging public housing blocks, some constructed in the 1970s. Initial results show a 40% reduction in water infiltration and associated damage. Water treatment facilities in Denmark have implemented bacterial concrete in containment structures, reducing leakage by 85% compared to conventional concrete structures of similar age. And in Japan, underground tunnel systems now incorporate bacterial concrete specifically engineered to heal after seismic events, addressing a critical vulnerability in the country's infrastructure network. The implications of this technology extend far beyond just fixing cracks. Concrete production accounts for approximately 8% of global carbon emissions, largely due to the energy-intensive process of creating cement. If structures last longer and require less replacement, the carbon footprint of our built environment could be significantly reduced. The World Economic Forum recently published an analysis suggesting that widespread adoption of self-healing concrete technologies could reduce global CO2 emissions by up to 1.4 billion tons annually by 2050, equivalent to removing 300 million cars from the roads. That's a significant contribution to our climate goals. Economically, the technology currently adds 2010 to 2035% to initial construction costs, but the return on investment becomes apparent within 7 to 10 years through reduced maintenance. Government infrastructure planners in several countries are now factoring these longer-term savings into their budgeting models, recognizing that the higher upfront cost pays dividends over time. The market for self-healing concrete is projected to grow from approximately $1.4 billion in 2022 to over $7.8 billion by 2030. This growth is driving further innovation and cost reductions through economies of scale. Material scientists predict that continued research will reduce the cost premium to under 8% within the next decade, making the technology competitive even for budget-conscious projects. This technology also addresses labor shortages in the construction maintenance sector. With many developed nations facing aging workforces and declining interest in construction careers among younger generations, self-maintaining infrastructure offers a partial solution to workforce challenges. The specialized skills required to develop and implement these advanced materials create new career paths that blend biology, materials science, and civil engineering, attracting a new generation of interdisciplinary professionals. Universities are already developing new programs that combine these disciplines, preparing students for careers that didn't exist a decade ago. Young professionals who might not have considered construction or civil engineering are now drawn to the field because of its integration with cutting-edge biotechnology. This workforce transformation represents not just a solution to labor shortages, but an evolution in how we think about infrastructure careers, moving from purely physical construction work to a blend of biological science, materials engineering, and digital monitoring systems. As bacterial concrete moves from experimental to mainstream, researchers are already developing the next generation of living building materials. Some laboratories are exploring concrete that can not only heal but also sense and respond to environmental conditions. Conductive bacterial concrete that can monitor its structural health is being developed at several universities, potentially eliminating the need for external sensors. Other researchers are working on bacterial concrete that can absorb air pollutants or generate small amounts of electricity through bacterial metabolic processes. The convergence of synthetic biology and materials science promises to transform our understanding of infrastructure from static, deteriorating assets to dynamic, responsive systems that improve with age. Future highways might repair themselves and de-ice automatically, absorb vehicle emissions, or generate energy from traffic vibrations. Buildings might regulate their temperature biologically or purify indoor air through living walls. The possibilities extend beyond concrete to other building materials, self-healing ceramics, metals with biological repair mechanisms, and composite materials that strengthen in response to stress. We're moving toward a future where the line between living and non-living materials becomes increasingly blurred, and our infrastructure takes on characteristics previously found only in biological systems. Despite its promise, the global implementation of bacterial concrete faces significant challenges. Regulatory frameworks in most countries weren't designed with living materials in mind, creating approval hurdles that slow adoption. Building codes and standards organizations are working to develop new testing protocols and performance metrics specifically for self-healing materials, but this process takes time. There are also technical challenges related to scaling production. The bacteria must be cultivated in controlled environments, encapsulated properly, and distributed evenly throughout the concrete mix, all while maintaining viability. Manufacturing facilities are adapting to these new requirements, but the transition requires investment and expertise. Cultural resistance within the conservative construction industry presents another barrier. Engineers and contractors who have worked with traditional concrete for decades may be skeptical of biological solutions. Education and demonstration projects are crucial to overcoming this resistance. Finally, there are regional considerations. Bacterial strains that work well in temperate climates may perform differently in extreme heat or cold. Researchers are developing region-specific bacterial concrete formulations tailored to local conditions, from the freeze-thaw cycles of northern regions to the salt exposure of coastal areas. Beyond the technical aspects, bacterial concrete represents a philosophical reimagining of our relationship with the built environment. For centuries, human construction has focused on conquering nature, creating rigid, static structures that resist natural forces. This new approach suggests a different paradigm, collaboration with natural processes rather than resistance to them. By incorporating biological mechanisms into our infrastructure, we're acknowledging that natural systems have evolved sophisticated repair and adaptation strategies over billions of years, strategies we can learn from and implement. This shift mirrors broader changes in how we think about technology and sustainability. Rather than seeing nature and technology as opposing forces, we're increasingly recognizing that biomimicry, the emulation of natural systems, often leads to more sustainable and resilient solutions. Bacterial concrete exemplifies this approach, using natural processes to solve problems created by conventional technology. This philosophical shift extends beyond materials science to how we conceptualize infrastructure itself. Rather than seeing buildings and bridges as inert objects that inevitably decay, we're beginning to envision them as quasi-living systems that respond to their environment, repair damage, and potentially improve over time. This perspective has profound implications for urban planning, architecture, and civil engineering, moving from a static to a dynamic understanding of our built environment. As this technology continues to mature and scale, we may be witnessing the beginning of a fundamental shift in how humanity builds its physical world. The quiet revolution of bacterial concrete represents not just a technical innovation, but a reimagining of infrastructure itself. Future cities might feature buildings that strengthen over time rather than weaken, roads that repair themselves after each winter, and bridges that communicate their structural health to maintenance systems. The integration of digital monitoring with biological repair mechanisms creates possibilities for truly smart infrastructure, systems that can detect problems, report them, and initiate repairs autonomously. This vision of responsive, self-maintaining infrastructure could transform urban planning and development, particularly in regions with limited maintenance resources. Developing nations might leapfrog traditional infrastructure models, implementing advanced self-healing systems that require less ongoing investment. The convergence of bacterial concrete with other emerging technologies, like 3D printing, advanced materials, and artificial intelligence, suggests a future where infrastructure is customized to local conditions, optimized for specific performance requirements, and continuously monitored and maintained through biological processes. We're moving toward a world where our built environment works with natural processes rather than against them, potentially transforming our cities into more sustainable, resilient, and adaptive systems. We stand at the threshold of a profound transformation in how we build our world. Bacterial concrete represents more than just a clever solution to cracking infrastructure. It embodies a fundamental shift in our relationship with the built environment. By harnessing biological processes that have evolved over billions of years, we're moving from an approach that fights against nature's forces to one that collaborates with them. The implications extend far beyond engineering and economics. As our infrastructure becomes more responsive, adaptive, and self-maintaining, we reshape our cities, reduce our environmental impact, and potentially create new relationships between humans and the structures we inhabit. The challenges ahead are significant. Regulatory hurdles, technical refinements, and cultural resistance must all be overcome. But the promise is equally profound. Infrastructure that improves with age, buildings that respond to their environments, and construction practices that work with natural processes rather than against them. This quiet revolution in concrete may well represent the beginning of a new era in human construction, one where the line between the living and non-living world becomes increasingly blurred, and where our greatest engineering achievements draw their strength not from conquering nature, but from embracing it. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.